Let's explore the key attributes of Saccharomyces cerevisiae that make it so valuable for bioethanol production. First, it has a high ethanol tolerance, capable of withstanding concentration up to 12 to 15% by volume. This allows for high ethanol yields without the yeast becoming toxic. Second, this yeast is incredibly robust, able to withstand a wide range of environmental conditions, including variation in temperature and pH. Moreover, Saccharomyces cerevisiae is genetically modifiable, which means we can enhance its fermentation trait to suit specific needs. This makes it possible to improve ethanol production efficiency and stress tolerance. Finally, its versatility is remarkable. It can ferment various carbohydrate sources such as glucose, sucrose, and starch. This flexibility allows for the utilization of different feedstock, making the bioethanol production process more adaptable and efficient. In safety and industrial contexts, the strain used in bioethanol production has been extensively studied and optimized. They are safe and non-pathogenic, posing no harm in industrial settings. This strain efficiently converts sugar into ethanol and exhibit high ethanol tolerance, making them ideal for large-scale bioethanol production. Moving on to the engineered enzyme used in our bioethanol production process, we have Rhizopus oryzae glucoamylase and Streptococcus bovis alpha amylase. Rhizopus oryzae glucoamylase is responsible for cleaving glucose unit from the non-reducing end of the starch molecule. This action is crucial in breaking down the starch into simpler sugar. On the other hand, Streptococcus bovis alpha amylase breaks down the starch chain into smaller fragments, making it easier for glucoamylase to act. Together, these enzymes efficiently convert starch into glucose, which is then fermented by the yeast to produce ethanol. By using this engineered enzyme, we can achieve simultaneous hydrolysis and fermentation. This means that the breakdown of starch into glucose and the fermentation of glucose into ethanol happen at the same time. This simultaneous action eliminates the need for a separate hydrolysis step, thereby enhancing the overall efficiency of starch hydrolysis and ethanol production. Additionally, this streamlined process can potentially reduce costs and simplify the production process, making bioethanol production more economical and efficient.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ethanol. I will present about the media. The pure native starch derived from corn, barley, wheat and grain along with the roots and also tubular crops can be utilized in additional process to produce bioethanols. The macro elements, micro elements and also growth factor are necessary in the productions of bioethanols. In this study, the sweet potato that contains starch will be broken down into sugar as the macro element, which is a carbon source using specialized enzymes such as alpha amylase and also amyloglucidase. It was decided that one alpha amylase unit represented the quantity of enzyme needed to generate 0.1 grams of reducing sugar, specifically glucose per minute. There are several micronutrients proposed in the productions of bioethanol such as iron, copper, zinc, manganese, calcium carbonate and also ferrous sulfide. All of these elements needed in small amount as mineral salt or trace element. Urea was a considerable growth factor for yeast, especially in the biosynthesis of amino acid, protein and also nucleic acid, and in other functions such as osmoregulations. Then, lastly, peptone also served as the primary source of nitrogen in culture media.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Nada Jasmine and I will be presenting on the chemical design. In general, biomass is composed of biogenic materials. It is regarded as unstructured matter and is often expressed in stoichiometric equations with an average biomass composition of CH1.8 or 0.5 and 0.2. Anaerobic Saccharomyces cerevisiae cultivation is a common cell culture method for producing ethanol, where biomass growth is directly linked to primary metabolic product synthesis, requiring only one equation to describe cell stoichiometry, with glucose as the limiting substrate, as shown in the equation. The basis for the calculation of stoichiometric coefficients S, B, X, P, G, D, and E is the balance of atoms C, H, O, and N. For 7 stoichiometric coefficients, 7 independent algebraic equations are in the disposal. The balance system is correctly specified. For ethanol production, can be redox balance as shown, where I is the number of component's free electrons, C is the number of carbon atoms of a component, Yi is the degree of reduction. The ethanol stoichiometric coefficient P is then P equals to 1530. Other unknown stoichiometric coefficients D, B, and E are found from the balance of atoms. The yield coefficient, gram over gram, of the total stoichiometric equation is also summarized in Table 1. The hydrolysis of the starch to glucose stoichiometry equations is as shown. Then, the ATP generated from the glycolysis of glucose will be the source of energy for the acerbic in the metabolic reaction of the fermentation. The stoichiometric equation involved in the fermentation is C6H12O6 equals to 2C2H5OH plus 2CO2, where values of glucose equals to 200 gram, ethanol 102 gram, and carbon dioxide of 88 gram. The yield of ethanol has been calculated, which is equals to 0.51 gram of ethanol produced over gram of glucose produced. The formula for kinetics on the growth of the cells immobilized and substrate is as shown below. The kinetics of the product ethanol can be mathematically described by the Monod equation, including without inhibition and with inhibition. To find the mu, to find the Monod max and Kx of the linearization method, Lineweaver-Burk can be applied. That is all for me. Thank you.
Assalamualaikum warahmatullah. My name is Fatah Nadira and I will present the mechanical design of the bioreactor for this project. According to the article written by Rivaldi, a batch strip-tank reactor showed the highest ethanol yield and volumetric productivity, which is 30% higher than the productivity in a packed bed reactor. Using a strip-tank reactor in the production of the bioethanol will offer several advantages, such as good temperature control, uniform mixing, and available process monitoring and control. Next, we decided to use immobilized cells in the STR for this project because immobilized cells have been demonstrated to produce better bioethanol yields than free cell. A study found that immobilized cerevisiae using calcium arginate generated 89.68% bioethanol, whereas free cells only produce 3.9% of bioethanol. The immobilized cells also increase fermentation efficiency, minimize contamination, and will enhance cell resistance against inhibitors. Next is vessel design. The figure on the right hand side is the general schematic diagram for the STR. First, the raw material medium, that is the sterilized potato starch, can be fed into the tank from the top using the sterilized attached tube. And second, the immobilized cerevisiae inoculant can be pumped through the column using a peristaltic pump until the desired volume of the media is achieved. And lastly, we choose round bottom because round bottom helps to eliminate stagnant zones, ensuring that the entire contents of the reactor are consistently mixed during operation. And we also add 4 baffles that can disrupt the formation of vortex that are occurring during mixing. And to improve the temperature control, we add additional methods such as heat jacket and internal coils.
Mixing is an important technique to obtain homogeneous nutrient and aeration throughout the bioreactor. The mixing efficiency can be obtained considering the essential parameters such as the impeller design for the stir-tank reactor. For the ethanol productions in the STR, a 6-flat plate turbine was chosen. The impeller, also known as the Russian turbine, that frequently well-known impeller in the fermentation industry, and the diameter of the impeller is usually 1 to 3 of the reactor diameter. This impeller has been well studied and is effective for the mixing and ethanol productions in STR. Moreover, 4 equally spaced baffles should be placed inside the bioreactor to break vortex and increase the mixing efficiency.
Assalamualaikum warahmatullahi wabarakatuh. I'm Misha Adrina. I'm going to talk about selection of pump and heater. So for pump, we use positive displacement pump for the reactor. This is because it ensures a constant flow rate regardless of the pressure variation in the system. This is important because we use potato as our starch and it can cause the liquid to become viscous. So we need a pump that can push through regardless of the pressure variation in the system. Next, for heater, it is important we have an indirect heater because it prevents direct contact between the heating element and the bioethanol reaction mixture, which avoids contamination and potential degradation of the product and also of the Saccharomyces cerevisiae. Now moving on to the design calculation for size of reactor, the nominal volume, which is the whole volume of the reactor, is 70 meter cube. And this was based from an article, but we have 20% headspace, so there's only 80% of working volume of the tank, so it is 56 meter cube. For agitator speed, it is 3 based on article, and for diameter and height, we have a height to diameter ratio of 3, so we obtain using the following equation, which means we got height as 3.76 meter and diameter is 1.25 meter. For impeller dimension, we use the impeller type Rushton turbine. So it's normally 1/3 of the reactor diameter. So we got impeller diameter as 0.42 meter. For pumping capacity, because it is Rushton turbine, we have an F of 0.72 and the pumping capacity is 0.16. For circulation time, we have 3 to 8.06, and for mixing time, using the equation, we got 97.56 seconds per mixing time. For tip impeller speed, we use the following equation and we got 3.96 meter per second for the impeller speed.
I'm Shamira. Now we will discuss the critical role of sterilization process. Sterilization is essential to prevent contamination and ensure successful fermentation for maintaining the purity of the final product. First, the fermenter and all associated equipment must be properly cleaned to remove any residual organic material, including parts, valves, and poop. This initial cleaning is typically followed by a rinsing step with water to ensure no cleaning agents remain. Sterilization can be achieved through various methods, including steam sterilization and chemical sterilization. Steam sterilization is the preferred method for fermenters due to its effectiveness and efficiency. The process involves exposing the fermenter to steam at 121 degrees Celsius or 250 degrees Fahrenheit for a period of 15 to 30 minutes. This ensures the destruction of all microorganisms, including bacteria, fungi, and spores, which might otherwise interfere with the fermentation process. The duration and temperature of the steam sterilization must be carefully controlled to achieve the desired sterility without damaging the equipment. After sterilization, it is crucial to cool the fermenter to the optimal fermentation temperature before introducing the potato starch substrate and the yeast Saccharomyces cerevisiae. During this cooling phase, maintaining aseptic conditions is vital to prevent contamination and ensure the dominance of our yeast culture. An alternative to steam sterilization is chemical sterilization, especially for heat-sensitive equipment, which involves using chemical agents like ethylene oxides, ethanol, sodium hypochlorite, hydrogen peroxide, or prussic acid. While chemical sterilization is effective, it requires proper rinsing afterward to ensure no toxic residues remain that could inhibit the yeast activity. Chemical sterilization can be a viable option when steam sterilization is not feasible, but is essential to ensure that all chemical residues are removed to avoid any negative impact on the fermentation process.
This is a summary of our mini design project, which has been thoroughly detailed and explained by the previous presenters.